All right, guys, so this is lesson, I think, 3.3. We're going to be getting into momentum, change momentum, conservation of momentum, and collisions. So here we go. So the first idea we're going to talk about is momentum, and momentum is just a measure of how hard it is to stop or turn a moving object. So it's like that idea of inertia and motion. So Newton's first law talked about an object that is moving, wants to continue to move in a straight line at a constant velocity. That second part is the momentum part. So the characteristics that make an object more difficult to turn or stop. So if you imagine, what are the factors that would make it more difficult to make something turn or make something stop? They are the two factors that are important in momentum, and they are mass and velocity. So the more massive something is, the more momentum it has, because you have more inertia. And then the faster it is moving, or its velocity, that is also dictating or an influence or factor on how much momentum it has. So the unit, and I didn't write this out here, but I will. The unit would be kilograms, because that's the unit for mass. And then you'd multiply that by meters per second. And it's a vector, so we have direction involved here too. So we have to worry about which way the momentum is going. So that's the ideas for that one. So continuing on, it says, here's a sample one. It says calculate the momentum of a 65 kilogram sprinter running east at 10 meters per second. So if we have this person and they're going east, so I'll just draw a dot or a circle, and they're going east at 10 meters per second, and their mass is 65 kilograms. It's a pretty simple setup. You just multiply those two numbers. So if you just multiply the mass times the velocity, you get the momentum. So the answer for this one is just 650. Again, the units would be kilograms meters per second. And you would state the direction it's going. It's going east. Generally, in our frame of reference, we draw east going to the right in our compass, so that would be okay as well. So positive x. You can have more than one object or in a system, and then you want the momentum of a system. So you're going to basically find the individual momentums and then use vector math to figure out the overall. So we already did the 65 kilogram sprinter running at 10, and we said this momentum in the last answer was 650. And then we need to know the momentum of a second person who is 75 kilograms. And they are moving at 9.5 meters per second. So again, it's just multiplication. So again, not a very complicated idea. For this second object, that green one is the second object and the red one was the first object. The momentum in the person running north would be something like 712.5 kilograms meters per second. I'm not worried about the units right now. So we have to combine them. So if you think about it, we have like 712.5 going up, and we have 650 going across. So, and these are vectors. So with vector math, you got to do trig. So we want the overall sum of those two together, the hypotenuse, which would be the total. So we would do the Pythagorean theorem, and we would do the inverse tan to get theta, which is what you would have to do to get the direction. So I'm not going to show all that work, but it's like a squared plus b squared equals c squared. So the answer that you should get, and we've done this a lot over the course of the class, so again, it should be familiar. The total momentum for this one should be 964.4 kilograms meters per second is the unit. And for theta, you would do the inverse tan of the y over the x, so it'd be the 712.5 divided by 650, second tan of that, and you should get 47.6 degrees. And you would describe it, this is going north of east. If you were using your x-axis, it would be above the positive x. I just used like their descriptions of this is going east, and this one was going north. Okay. We'll have some more opportunities to do the Pythagorean theorem and those ideas. So we'll practice that a little bit more, but that's what you should have gotten if you work through that problem and get the answer. So we have momentum, and that's our first concept. We just kind of talked about how to calculate that. We also have change in momentum. So change in momentum is triangle P. Change in anything is delta, and then P is momentum. So change in momentum, and just like you do for anything else, you take the final value minus the initial value. So if you know the final value and then initial value, you can figure out how much it's changed. Again, it's a directional idea. It's a vector, so make sure that you are considering the direction with like positives or negatives to represent how it's moving. All right, this is a demo that I'm going to do in class. I'm going to hold on to this one, and we'll come back to it in class. But another word for change in momentum is impulse. So impulse is the product of an external force for a time, which results in a change in momentum. So impulse, J is the symbol for impulse, is force times time, or duration of time, so it could be triangle T. They're the same thing. So it's just really another way to describe the change in momentum as the impulse. So you can do the final minus initial, which is what we just first learned on the last slide. So the final momentum minus the initial momentum, or it's the force times the change in time. If we go back to the chair example, if you remember in class, I pushed a chair. The chair initially maybe was at rest, and I applied a force, F, for some duration of time, delta T. So when I started pushing until I stopped pushing. And by the time it got to the end of that time, the chair was moving. So it had some velocity going that way. The chair always had mass. So the idea is that like you can measure the change in momentum through a force times a time, or you could just, if you know the initial and the final values, you could figure out the change in momentum directly through subtraction. So both these equations will work. We get a new unit for momentum or change in momentum. They're the same unit. So a kilogram meter per second or a newtons times seconds or newton seconds. They're the same thing. So they're the same equivalent units, just whichever one you want to use. You can use either one for momentum or change in momentum. Again, direction for both is important. So you have direction. So if I had the force going to the right, the change in momentum would go to the right. And if I had the net force going to the left, the change in momentum would go to the left, or up, down. Whichever way the force is going is the direction for the change in momentum. All right. Just talking about impulsive forces real quick. Impulsive forces are ones that are usually high in magnitude, so they're large forces, but they only last a short period of time. So if you imagine this baseball being thrown in, it's got some initial momentum going in. The bat hits it, and it's got some final momentum going out. There was an impulse or change in momentum, or J. You could write it as J. It doesn't really matter. But I usually just write change in momentum. There was a change in momentum, and that's because of the force of the bat on the ball. So the force times the time. And that force is usually pretty big. So like if you imagine a baseball bat hitting a ball, it's a big force, but it's a small period of time. But you get a change in momentum there. All right. Another way you can look at this is on a graph. So this graph has force versus time. And this time is in milliseconds. We could convert it to seconds. It would be like 0.001 or 0.002. So again, you can imagine like this is going from a thousandth of a second, from 0.02 to about 0.03. To find the impulse, again, our equation for impulse or change in momentum is force times time. So if you take the area of the shape, and we've done areas before, this looks like a triangle. So we would get the change in momentum if we know how long this force is acting for the time period, and we knew the height, which would be the amount of force. And you'd have a triangle here, so you'd do 1/2 base times height. The reason why it's a triangle, basically, if you think about things hitting, so if we imagine the baseball and the bat again, so this is the ball, and I don't know, I'll draw a blue bat. So if this is the blue bat hitting the ball, if you imagine the contact, as the ball hits the bat, the force is like, so when they're not touching, there's no force. So that's what that baseline is here. When it starts to hit, it starts to increase. So like it increases up to the point, And then why does it decrease? It's because it starts moving off the bat. So like as it loses contact with the bat, it drops down and goes back to 0 because there'd be no force when they're not touching. So that's why it's a triangle in shape. So it's usually like this big spiked triangle that's really narrow in width, but it's very high in force. So that's the impulse idea. Okay, so the biggest idea that we're going to talk about in this video is the law of conservation of momentum. So the law of conservation of momentum, pretty similar to all the other conservation laws that you've had. So we talked about the law of conservation of energy in a previous lesson, and it basically said the total energy in the beginning was equal to the total energy at the end, as long as it was like a closed system or there weren't any energies kind of going in or out or any external forces. Same idea here, it's just talking about momentum. So it says if the resultant external force on a system is 0, so if there's no external forces, then the vector sum of the momentums before the collision or before something happens should be equal to the momentum afterwards. So again, sigma just means add, p is the momentum. So you're going to add up all the momentums before. Generally, we talk about collisions. We talk about law of conservation of momentum. So if we talk about all the momentums before a collision, and there's no external forces in our system, then that would be equal to the total momentum after. Okay, so the key to kind of think about this and make sure you understand it is if you're talking about external versus internal forces. So external forces can definitely change the momentum of a system, but internal forces cannot because they're containing the momentum within them. So two examples to distinguish between those. So if you imagine a golf ball on a tee. The golf ball is our system, so that's the thing we're worried about the momentum of. The golf ball is not moving if it's at rest on the tee, so it's got no momentum to start. You're going to hit it with some sort of club, a driver, or whatever it is, and because of that, the driver is going to apply a force for some period of time, and the ball is going to start moving, right? So that force acting on the golf ball is imparting momentum into it. So it goes from no momentum to some momentum, so there was a change in momentum, okay? So that idea is an external force. Internal forces cannot change the momentum of the system. So like if you ever played pool and one ball is going to go run into the other in what's called a head-on collision, this ball might be at rest before and this ball is moving before, so it's going kind of like this. So that's like we could figure out the total momentum by taking the momentum of each piece and adding them together. Afterwards, this 7 ball might stop and the 8 ball might start moving, and that would be conserving the momentum because it would just transfer the momentum from one object into the other, but it's keeping it all in our system because we consider both objects to be part of our system. Okay, so it's just like how you consider an object or a system, similar to what we did with the energy idea. So if you include more things in a system, then it's probably going to conserve. If you only look at one item, then it might not conserve, and it would be some sort of change in either energy, and in this case, it'd be a change in momentum. All right. So another idea, which is not exactly a collision, but it's kind of the reverse of a collision, is something called an explosion. So an explosion is when suddenly you have internal forces that cause things to move out. You guys can imagine what an explosion is. And momentum is conserved in an explosion because it's all internal. So you would also notice there's an increase in kinetic energy that comes from the potential energy being used up, converting chemical energy into kinetic energy within the system. Okay, so it's got stored energy in it. Another example of an explosion would be recoil. So if you've ever fired a gun or if you've ever seen a cannon being fired, that kind of propulsion backwards, that's that kickback, that's the recoil. So so if you imagine sort of the situation, if you had a gun or a cannon or whatever it might be, and a bullet. So we got our bullet inside of our gun here. And they might both be at rest to start. And then afterwards, the bullet is obviously going to go forward and to the right, and it's got some momentum. If we had no momentum in the beginning, so if we add up all the momentum, sigma p in the beginning, initial, if that's 0, the total momentum at the end, final, has to be 0 as well. So if the bullet gains momentum going to the right, the gun, there we go. The gun has to gain momentum going the opposite way. And these two momentums would have to cancel out. So they should be the same length. The velocities might be very different because their masses are different, but the idea is that the internal forces are acting on both things for the same amount of time, so the change in momentum for each piece would be the same. So the force and the time are the same. They're just, the force is an action-reaction pair. So one on the bullet, it's going to push, the gun pushes the bullet to the right. The reaction would be the bullet pushes the gun to the left. And they act for the same time, so you get the same change in momentum. One's just positive and one's just negative. And that makes sense, right? So if you had a gain of momentum or a positive momentum of the bullet, you'd have an equal and opposite negative momentum of the gun, and the total momentum would still be 0. So let's try this problem here. And it says a 5 kilogram projectile launcher, which we'll just call L for the launcher. That's the mass of the launcher, ML. Shoots a 209 gram projectile at 350 meters per second. So this 209 grams, we don't work in grams, so the mass of the projectile would be 0.209 kilograms. And this would be the velocity of the projectile final. Okay, it says what's the recoil velocity of the projectile or launcher. So again, if we drew kind of a similar picture to what I just had before, so this projectile is at rest inside the gun before. So the initial condition over here in this picture, again, draw a picture. The momentum total, so the sum of the momentum initial, is 0 because nothing's moving in the beginning. Afterwards, the sum of the momentum, in order to be conserved, which it should be because there are no external forces, the final total momentum should be 0. And the way that works is the gun or projectile launcher is going to go the opposite way to the bullet. So they're going to go opposite directions. So we're going to just set up this conservation of momentum idea. So the total momentum initial equals the total momentum final. You could just write total, but this sigma is like a shorthand version of saying that. So again, in the beginning, nothing's moving, so this is all just 0. At the end, we have 2 things moving. So we have the momentum of the launcher final, and we have the momentum of the projectile final. So again, you're just using standard P equals mv to solve for whatever you're looking for. So if we have 0, we know the mass of the projectile launcher is 5, and we don't know the final velocity of the launcher. So VLF or VFL would be the final velocity of the launcher. For the bullet or projectile, we know that's 0.209. And we know it's going at 350 meters per second. So that's pretty fast. It's really fast, actually. So if we do this math, we got 0 equals 5 VLF plus 0.209 times 350 is 73.15. We got to solve this, so I'm going to take the 5 to the other side. The 5 VLF becomes negative. And then you divide through by 5. Negative 5, excuse me. So VLF, the velocity launcher final, is negative 14.63 meters per second. So that's a pretty big velocity. So this is a pretty big explosion that's going to make the bullet go that fast. And that's the kickback, that's the recoil. So you've probably seen videos on YouTube of people trying to fire shotguns or big handguns and them like flying backwards and hitting them in the face and things like that. If you haven't, it's kind of amusing to watch. So anyway, that's kind of physics of that. We could also have momentum in multiple directions. I'm going to skip this one because it's a little more complicated than I think what we need to do right now. But it basically, if we think about the idea, so we have this object and it's going to explode into 3 pieces. So piece one, piece 2, and then piece 3. So it says piece 1 goes north, piece 2 goes east, and we got to figure out which way the third is going. So V1 final would go up, V2 final would go to the right, and then we need V3 final. So we're looking for V3 final. Looking at this, I would expect 3 to go that way. Like that's what I would expect to happen. And the reason why it has to do that is because before anything starts moving, the total momentum was 0. So this piece is going to go up. This third piece is going to have a portion of it that's going to go down in the Y. And then this one's going to the right, so this one's going to have some going to the left. So that would be a negative X. So this one's going to go down to the left. And you would just do conservation of momentum in each direction. So momentum is conserved in each direction here. So you'd have the final and initial for the X. And then you do basically the same thing for the initial in the Y and the final in the Y. Maybe I will go ahead and finish this one up because we don't have too much left. So looking at this, again, everything in the beginning is at rest. So there is no momentum in the X. There is no momentum in the Y. Afterwards, you just have the pieces that are moving. So we have piece 1, which I said is 2 kilograms at 200 meters per second. So 2 times 200, that'd be a positive 400. Plus, and then the second piece would be P3. So 3 is 3 kilograms. So it'd be 3 times V X final for 3. So it's final velocity at 3. So you divide both sides by 3, and then you'd take it to the other side. So V final in the X for 3 turns out to be a negative 133.3 kilograms, and it's going to the left. So that's 133.3 meters per second going to the left. For the Y, it actually turns out to be the same number because in this one it's 4 times 100, so that's 400, and we still have the 3, and this time it's VYF per 3. So we're gonna do the same math and divide through by 3. So VFY turns out to be negative 133.3. So we have our 2 components. We have 133 going to the left, and we have 133 going down. So we need to find out, okay, what's that overall final velocity, and what's this angle theta? Again, we would do the Pythagorean theorem. So a squared plus b squared equals c squared. So when you do this, you should get 188.56 for the velocity amount, so meters per second. And then that's at an angle of 45 degrees because they're the same. So if it's the same X and Y components, that's a 45 degree angle. Tan of the same number, tan of 1 is 45. Okay, so I think I'm going to probably stop there because we haven't got to collisions yet and this video is getting longer. So I'll stop there and we'll get into collisions next.